All right, let's get right into it. For, decades, the way we've built physical things, we're talking cars, robots, all those gadgets in our homes, has followed a super rigid, very predictable path. But something big is bubbling up under the surface. A quiet revolution is happening, and it's borrowing its playbook from the world of software to completely change how we make things in the real world. This is about creating hardware that can actually learn, adapt, and get better long after it's left the assembly line.
To really get what this shift is all about, you have to look at Boston Dynamics' Atlas robot. So picture this. In the lab, during a test, it stumbles, and bam, it falls flat. Now, in the old way of thinking, that's a disaster, a catastrophic failure. But for this team, nope. It was a gold mine of data. We're talking hundreds of data points on balance, momentum, and recovery. The big idea here is that failure isn't a dead end anymore. It's just really, really good data.
And that one moment, it just perfectly captures this whole new mindset. The fast, iterative, learn from your mistakes approach that built the apps on your phone is now being used to build hardware. But here's the catch. For physical products, the stakes are so much higher. I mean, think about it. You can't just push a software patch to a robot that's already toppled over, right? So to really appreciate just how big this change is, we need to take a quick look at the old playbook. For a long time, hardware development has been stuck using a process called the waterfall method. This slide really lays it all out, side by side. On the left, you've got waterfall. It's a rigid, one-way street. You plan every single detail up front, and if you make one mistake late in the game, it can send you all the way back to square one. It's slow and expensive. But on the right, that's Agile. It's a continuous loop. You build, you test, you learn, and you repeat. It's all about being fast, flexible, and ready to embrace change. Right, and that's the million-dollar question, isn't it? You can't just hit undo on a piece of metal like you can with a line of code. Applying a software philosophy to the world of atoms, not bits, comes with some very real, very serious challenges. And here they are, the big hurdles. Getting feedback takes way longer. You have to actually build a physical thing to test it. The stakes are, of course, much higher. A software bug might crash your app. A hardware bug could cause actual physical harm. Then you've got to integrate all these complex physical parts, deal with strict safety regulations, and you're at the mercy of global supply chains. It is a whole different ballgame. So, given all those challenges, you might be wondering, how is this even possible? Well, teams all over the world are figuring out some absolutely incredible ways to make it work. Let's look at a few real-world examples that are just knocking it out of the park. First up, bio-inspired robotics. This is where engineers are looking to the natural world for clues. And it makes perfect sense, right? Evolution is the original agile process. We're talking billions of years of trial and error, where every single generation learns from the one before it. So how does this actually work in a lab? Well, take MIT's soft robotics group. They built a robot that mimics an elephant's trunk. They didn't try to build the whole complex thing all at once. No way. They worked in short, 2-week bursts called sprints. One sprint might focus only on grasping an object, the next on navigating a simple maze. You had biologists and engineers working side by side, using AI to crunch the data after every single test. That data then told them what to focus on in the next sprint. It's pure agile, in the flesh, or, in the silicon. Okay, so let's zoom out from the lab and head straight onto the factory floor. We're not talking about those old, dumb robots just welding a car door over and over. We are talking about the entire factory operating like one big, adaptable team. And this gets to the core of what's called agile manufacturing. There's this electronics producer in Shenzhen, for example, that uses humanoid robots that learn entirely new assembly tasks every single week. This means they can reconfigure their entire factory for a brand new product in just a couple of days, not the weeks or months it used to take. Production is planned in these short cycles, and AI is constantly looking at the data, suggesting ways to get even better. And for our last example, let's look at the Internet of Things, or IoT. We're talking about all those smart devices that have to make decisions out in the messy, unpredictable real world. The secret sauce here is something called Edge AI. All that means is the smarts are happening on the device itself, not somewhere far away in the cloud. This makes them way faster and much more reliable. And the results? Well, they really do speak for themselves. One smart thermostat company used these agile sprints to tackle specific customer wants, like saving energy.
By constantly testing and updating their AI based on real data from millions of homes, they achieved energy savings that were 25% higher than their target. And get this, customer satisfaction shot up by 40%. They were literally learning from their users in real time.
Okay, so we've seen why this is happening and where it's working. Now let's get practical. What are the actual strategies and tools that are making this whole revolution possible?
So how do you iterate quickly and safely with actual hardware? Well, you have to be really smart about it. Teams are all in on simulation. They create what are called digital twins, perfect virtual copies of their products, so they can test 1,000 bad ideas safely and cheaply in a digital world first. They design for modularity, think Legos, so you can swap one part out without having to rebuild the whole thing. And crucially, safety isn't the last step. It's a core part of every single sprint from day one.
And of course, you need the right tools in your toolbox. A whole ecosystem of tools has popped up to support all of this. You've got platforms like ROS, which is like an operating system for robots. Video game engines like Unity are being used to build those incredibly realistic digital twins for testing. And powerful little AI platforms like NVIDIA Jetson allow devices to make those smart decisions on the edge. All these pieces together form the backbone of physical agile development.
All right, let's zoom all the way out. What does all of this, the new mindset, the cool examples, the powerful tools, what does it all really mean for the future of the things we build and use every single day?
The big takeaway is this. The shift to Agile for physical things isn't just about building stuff faster or cheaper. It's about creating a fundamentally new category of product. We're no longer just building things that perform a static function. We are building intelligent systems that can actually learn from their environment, adapt to new challenges, and get better all on their own.
And that leaves us with a really fascinating question to chew on. If the physical objects all around us, from our cars to our coffee makers to the factories that build them, are no longer just static things but are dynamic, learning systems, what does that mean for how we live and work? The possibilities are just now starting to unfold, and honestly, it's going to be an incredible ride.